Welcome to the CPU and registers overview video. The basic function of the CPU, which is the central processing unit, is to execute a program correctly. So, in order to execute a program correctly, it must be able to access the three types of memory we have already discussed. It needs to be able to perform calculations through the arithmetic and logic unit, and it needs to control and monitor peripherals through the input-output registers. It also needs to handle interruptions and controlling itself in order to keep track of its operation. This is achieved through a register that is called the program counter. Let's have a look at the block diagram of the AVR architecture. This is the block diagram of our CPU. This is one of the most important parts of our CPU, which is the arithmetic and logic unit. Another important part is this section over here, which is the general purpose registers. It says that it is a 32 times 8 section, which means that we have 32 locations and each location is 8-bit wide. Over here we have the program counter. We will see this section later on this video. Another important part is the instruction register, which, as you can see, it's actually connected to the program counter and the flash memory. And the instruction register holds the current instruction to be executed by the CPU. And the instruction decoder, it's a specific part of our microcontroller which decodes or translates the instruction, which is the instruction comes in binary or in zeros and ones, and it decodes this instruction in order to know what the microcontroller needs to do. Another important part that you need to take a close look at, it's these words which say direct addressing and indirect addressing. And basically what they do is they access the data stored in the static RAM. Let's see an important component of the CPU. This component is the ALU, and as the datasheet says, it supports arithmetic and logic operation between registers or even between a constant and a register. Single register operation can be executed in the ALU. It is important that you understand that after an arithmetic operation, the status register is updated to reflect the information about the result of the operation. Be careful. The status register does not hold the result of the operation. It reflects information about the result, but not the result itself. The ALU has three types of operations. The arithmetic operations, such as sums, subtraction, multiplication, logic functions, such as AND or XOR operations, and bit functions in order to see, for example, if a bit is on or off. A very important component of the ALU is the status register. So what is a register? A register is nothing but a special group of 8 bits with special addressing characteristics. These registers are stored at SRAM. The categories for these registers are general purpose registers, which of course we have 32 registers. We also have input-output registers, which can be 64 easy access registers and up to 160 more extra registers. And we also have some registers that are not, or that we cannot access directly. Let's see some examples. The general purpose registers are named from register 0 to register 31. Inside those 32 registers, we also contain 3 special registers, which are actually 16-bit wide registers, and they are used for indirect addressing. Register 26 and 27 correspond to register X. Register 28 and 29 correspond to register Y. And register 30 and 31 correspond to register zeta. Inside the EO register, we have some of the following registers. One of the most important ones that we were already discussing is the CPU status register. Another register is the stack pointer, which we will be explaining on this video also. And we also have some other registers for peripherals such as timers ADCs, etc., which we will cover when we talk about some specific peripherals on other videos. About not directly accessible registers, we have, for instance, the program counter, which we will be covering on this video. The transmit shift register is another example. This register is for communication. As you can see, not all these registers are 8-bit wide, such as X, Y, and Z. Also, the program counter is not an 8-bit wide register. Now let's have a closer look to the general purpose registers. This is what the memory looks like. As you can see, we have addresses starting at address 0 and ending at address 1F in hexadecimal. You can see that we have the number 0 and 7, which is the number of the bit inside those addresses. You can also see that starting from register 26, we have the X register low byte, and ending at register 31, we have the Zeta register. The register file supports several operations or several types of operations inside the ALU or inside the CPU, which are the following. For instance, we can sum or we can add two registers. Each register is an 8-bit wide register, and the result is also going to be an 8-bit wide register. But for instance, we can have a multiplication where we have two 8-bit operands, but the result is going to be 16-bit wide. Something that you need to know is that we will usually start using register 16 for some operations, since some instructions or mnemonics restrict the use of register 0 to register 15. For example, the mnemonic LDI, which stands for load immediate. This register loads a constant to a register, but it cannot store something or load an immediate constant from register 0 to register 15. It can only load information to register 16 through register 31. This is a closer look to registers X, Y, and Z. As you can see, the X register has the low part, which is this one here, and a high part, which is this one here. Those two registers combined form a 16-bit wide register. That also applies to register Y and register Z. These three registers are used for indirect addressing of the data space, although they are also used for accessing flash, which is the instruction space. Now let's talk about the status register. Status register contains the information about the result of the most recently executed arithmetic instruction. Remember, it is not the result, but information about the result. This information can be used for altering the program flow in order to perform conditional operations. Just a note, we don't have the if, while, and for instructions in the microcontroller, but we can do something like those instructions with another instructions. A very important fact about the status register is that it is updated after all ALU operations. What it means is that if you care about the result of an operation and you perform another operation, then the status register is going to be erased and written with the new information. So you need to be very careful about when to read the status register. Another thing to consider is that the status register is not automatically stored when entering an interrupt routine. It is also not restored when returning from an interruption. This must be handled by software. We'll be seeing this better in another video when we learn about interruptions. This is the status register. As you can see, it's called SREG and it has 8 bits. And we can see over here that we have all the bits numbered from 0 to 7. The 0 is the first bit and the 7 is the last bit. Or we will be referring the number 7 in a case of an 8-bit register as the most significant bit. Another thing that you need to see is these two things, the read-write property and the initial value. As you can see, all the 8 bits in this register has the words R/W, which means that all the bits starting from bit 0 to bit 7 have the capability to be written and to be read from. Also, we have the initial value. The initial value for this register, it's that all bits are 0. So what is the function of these 8 bits? Let's start from bit number 7. Bit number 7 is the global interrupt enable. When we put a 1 in this bit, we enable interruptions. The next bit is the T bit. This is used to store and load information from some other specific bit. So for instance, if we want to store the status of let's say a sensor, if it is 1 or 0, we can use this temporary space, which is again the bit T. All these bits are called flags. This flag is a half carry flag and is used for arithmetic operations. Let's assume we have the number 8 in binary, which is 00001000, and we want to add to this number the same number 8 in binary. So when we start summing, 0 plus 0 is 0, 0 plus 0 is 0 again, 0 plus 0 is 0, but then we get the 1 plus 1, and 1 plus 1 is 2, which in binary is 1, 0. So 1 plus 1, the result is 0, and we carry a 1 to the next column. This is what is called the half carry. Why it's half? Because it's happening in the half part of a binary number. And of course the result is going to be a 1 here and also zeros. But again, the importance is not on the operation, but on what happened exactly at the half of the byte. We carry a bit from bit number 3 to bit number 4. That is what the half carry does. The next bit is the sign bit, which is an exclusive OR between the flags N and V. So let's talk about flags N and V, and then we will come back to the sign. The V stands for the 2's complement overflow flag. This flag, it's going to indicate to us whether a negative number is overflown. The maximum capability of an 8-bit negative number is minus 127. So what it means is that, let's suppose you have minus 127 and just subtract a 1. So it would be minus 127 minus 1. The result would be minus 128. Since that number does not fit in an 8-bit variable, this flag would be 1. The next is the negative flag. The negative flag, it's very easy to understand. If you have a number which is 0f, the negative flag of this value would be 0. Why is that? Because the most significant bit, which is the first bit of this digit, is a 0. However, if you have a number that it is 80, for example, the number 8 has a 1 in the most significant bit, so the negative flag would be 1. Now let's go back to the sign flag. The sign flag is the exclusive OR between the negative flag and the 2's complement. The way that you are going to understand this better is that if this bit is turned on, the number is negative. What this means is that sometimes the negative flag can be off, can be 0, but still the correct number is negative. So the sign of a number depends on two things: whether it's negative, which is the N flag, or whether it has overflown and it's showing us as though the number was positive, but it's actually negative. This is what the S flag does. Next we have the 0 flag. This is the easiest flag to understand. The Z flag tells us if a number is 0. If a number is 0, the zeta is 1. If a number is different than 0, then the zeta flag is going to be 0. And finally we have the carry flag. The carry flag is very similar to the half carry flag. However, the carry flag is when we have an overflow from bit 7 to bit 8. Let's see an example. Let's suppose we want to sum 128 plus 128. This is the binary representation of those two numbers. Of course, we start with the first column, it is 0, and again 0, and we can see that all the results are going to be 0. And when we reach the last column, we see that we have a 1 plus 1. Again, we saw that 1 plus 1 is 0, but we have to carry a 1 to the next column. This 1 over here, it's the carry flag. If a carry is 1, our number does not fit in an 8-bit number. It needs 9 bits at least. So we need to be careful. If we have carry equals to 1, it means that we have a bigger number than our 8-bit number can store. Now, just a note, this is only one input-output register. Again, this is a status register. Each register has 8 bits, and we have a possibility of 64 easy access register plus another 160 maximum registers. So we have a lot of information, and that information, of course, is in the datasheet. But it is important that you understand that this is one of the most important registers. However, this is only one register. Now, let's talk about the program counter. This is another register. However, this register it's not user accessible, so we cannot easily read this data. This program counter is 14-bit wide for our microcontroller, which is the ATmega328. This register holds the address of the current instruction being executed. Let's see an example. Let's suppose we have the flash memory. Remember, this is the flash memory map. So let's suppose we have some instruction at address 0. As you can see, we have address 0 and it says instruction number 1. This could be any instruction. Next, let's assume that at address 63 in hexadecimal, we have the instruction number 100. Again, this instruction can be anything. So example, if the program counter is equal to 63 in hexadecimal, then what it means is that the current instruction being executed by the CPU is the instruction number 100, because the instruction number 100 is stored at address 63 in hexadecimal. However, we have to be very careful. Not all the instructions fit into one location. Some may take 2 addresses or locations. In this example, we are assuming that all instructions fit in one location. Now, we need to talk about the stack. And before telling you about the specific register of our microcontroller, I want to tell you what is a stack. Imagine you have your desktop, have some workspace over here, and someone hands you a piece of paper, and you put the piece of paper on this part of the desktop. Next, another person hands you another piece of paper, and what you start doing is you start putting the pieces of paper one on top of the other. This is what we call stack. At the end of the day, you may have something like this, which is all the pieces of paper that were given to you throughout the day. Now we need to talk about the stack pointer. As you can see, the stack pointer is a 16-bit wide register. Wide, if you can see in this image, we have from bit 0 to bit 15. Also see that all bits can be read or written, and the initial value of the stack pointer is 0. Now, the main use for the stack pointer is for storing temporary data. For example, to store local variables, and it is also important for storing the returning addresses after some interrupt happens or some subroutine. The stack pointer is always going to point to the top of the stack. Another thing that you need to understand is that the stack is always going to be pointing to the RAM. And the stack pointer also must be defined by the programmer before any subroutine calls are executed or interrupts are enabled. The stack pointer must be set to point at least above the input-output registers. Let's see an example of what is the stack and what is the stack pointer. It is important that you understand that these are two concepts. One concept is the stack, which is, let's see, for example, the stack of papers. And another thing is the stack pointer, which we'll be seeing on this example. The stack pointer is recommended to point to RAM end. RAM end is the last address of the internal RAM of any microcontroller. In the case for the ATmega328, the RAM end is 8FF. Now, what is the stack? In this case, the stack it's the 5 locations that you see on this image. The stack pointer is the arrow that you are seeing. The stack pointer tells you where you are now in the stack. Those are the two concepts. Again, the stack it's the locations and the arrow it's the current location. So how does the stack behaves? First, let's assume we are using an instruction that is called push. This instruction, what does, it stores data into the stack. So right now the stack is 85F and we have stored some data. What's going to happen? What's going to happen is that we're going to put some data on the first location, which is 85F, and the stack pointer is going to be modified because we need to know where we can store some other data. So once we store, this is what happens. What we're seeing there is that some information got stored and the pointer changed because now we have the option to store some new data, but we need to store it somewhere else. We cannot store it on the same location. Now let's assume we do the same. We're going to store some other data, and what you see is that once we store this data, the stack pointer again it's modified to be able to store some new other data. Again, we store another data, and this is what happens. Now this is the process of storing data. We have stored three information or 3 constants, or it can be anything, but we have stored 3 things. Now what happens if we want to retrieve them? Well, we have another instruction that is called pop, and this instruction what it does is that it retrieves data from the stack, but it's important that you understand that it retrieves the last information that you put into the stack. When you do the pop, you're going to get the information from address 85D. In this case, I'm putting it in red because we have already read that information, and you can see that the stack pointer becomes 85D. Just to clarify, the stack is the whole space that we can store data to, and the stack pointer is the arrow that indicates where we can store new data. Be careful, this arrow again indicates where we can store new data. This means that if we want to read some other data by using another pop instruction, we're actually going to get the address 85E because 85D is the space for new data. The stored data is at A5E. Thanks for watching. I hope you understood the concept of this video.